Hello, welcome to the calculations of pi. I'm going to do three different ways of calculating pi. Two of them use calculus using the limit method, and the other one uses a probabilistic method. So hopefully this would be instructive and informative. I hope you enjoy it. So one second. Hi, so let's see if this works. One second. So remember, pi is a mathematical constant. It is used in geometry to calculate areas and perimeters of circles, right? So let's start with the definition of pi, right? So pi is a number that has about 3.14, 15, 1, and so on, right? First thing that we know about pi is that it's a transcendental number. Okay, so what does that mean, right? It means that it cannot be the root of a polynomial equation over the integers or over the rationals. So, but it is indeed a real number. Um, so yes, right. So that's what that means. Right. Transcendental numbers are difficult to prove that they're transcendental, right? So the proof of pi being transcendental requires a lot of mathematics, and it's not straightforward, actually. In fact, it's difficult to prove something is transcendental. It's easy to prove something is algebraic because all you got to do is come up with a polynomial equation whose root is that number, right? Transcendentality is its own research area, actually, but there are some proofs available that you may find online if you're curious. So, all right. So let's do method one for calculating pi. We're going to use the perimeter, right? Method. And the idea is simple, right? So if we draw a circle, right, we can draw an equilateral triangle on it, right, and calculate its perimeter. Next, we can draw a circle and draw a perfect square in it, right? Next, we can draw another circle and then draw a pentagon, right? A regular pentagon in it, right? And then we can draw another circle, right? And draw a hexagon, a regular hexagon, right? The idea is that the perimeter and the area of these regular polygons circumscribed in, I'm sorry, I can't say that word, circumscribed inside this circle eventually approach the area of the circle and they approach the perimeter of the circle, right? That is, the perimeter of the triangle is an approximation to the perimeter of the circle. The perimeter of the square is a better approximation of the circle, and so on. The hexagon has an even better approximation, right? So that's the idea, right? So keep drawing circumcised or circumscribed. Yeah, that's how you say it. Circumscribe regular polygons inside the circle and calculate the corresponding perimeters and areas. And the idea is that eventually those areas and perimeters approach the perimeter of the circle and the area of the circle, right? And at the very end, we can calculate pi by looking at the limiting method. This will give a function that formula for a trigonometric function whose limit approaches the value of pi. So yeah, so let's do the most. So let's do the perimeter method. That is, let's calculate the perimeter of the nth regular polygon, right? So n-gon circumscribed inside the circle, right? And what I'm going to do is do a calculation. So I'm just going to think of the regular polygon as being sliced into a bunch of isosceles triangle, right? So if you notice here, right, this is an equilateral triangle, so it's isosceles, right? However, the square can be split up into 4 isosceles triangles, right? Which are those guys? The pentagon can be split up into 5 isosceles triangles, right? The hexagon can be split up into 6 isosceles triangles. Now, the triangle, the equilateral triangle inside the circle can be split up into 3 isosceles triangles, right? Right. So, in the most general case, an n-gon that's circumscribed inside the circle can be split up into n, capital N, isosceles triangles of the same shape and form, or congruent isosceles triangles in geometrical terms. So what I'm going to do is draw the circle itself and draw a genetic slice, right, which is going to be isosceles, right? And we're going to draw its angles theta. The both sides of the circle, I mean the both lengths of the isosceles triangle that have the same length are the radius of the circle, right? And I'm going to draw that, so there's capital N slices that are congruent and are isosceles. I am not sure why I did that. So it's because I did that, so N slices, they're isosceles. And I'm going to draw that here so that it's easy to see, right? So this is theta. This is the other side of the circle, right? As where theta in this case, right, is equal to 2 pi over capital N. And the size of the isosceles triangle is going to be r, right? Now, if I do this correctly, I want to calculate the perimeter, right? Something's going on here. There we go. So the perimeter of this isosceles triangle is going to, I need to calculate this length right here, right? Well, I know this is theta over 2, right? Which is equal to pi over n, right? This is r, so that means that I can calculate this length using the sine formula, right? So sine of theta over 2 times r is going to be b over 2, right? The base over 2. So this is going to mean that the base itself, right, of this isosceles triangle is going to be twice r sine of pi over n, right? Capital N. Now, there's capital N slices. So if I multiply capital N times b, right, I get 2 n r divided times sine of pi over n, right? Now, this is going to be the perimeter approximation to the perimeter of the circle. Right? So now what is pi, right? Remember pi, I'm going to define that to be equal to the perimeter of circle, right? Divided by the diameter. Okay? In this case, it's approximately equal to capital NB divided by the diameter, which is 2r, right? So this is going to be equal to 2r capital N sine of pi over n divided by 2r, right? So I can cancel the 2r, and the approximation from the perimeter calculation, right, of the circumscribed regular n-gon is going to be n sine of pi over n, right? So this is going to be the nth, capital Nth approximation to pi. Now we're going to use some calculus, right? So to figure out what is the limit as capital N goes to infinity, and we're going to show that it is indeed equal to pi. So yes, so the limit as capital N goes to infinity of pi capital N, right, is going to be the limit as capital N goes to infinity of sine of pi over capital N divided by 1 over n, right? Now, as n goes to infinity, right, the top goes to sine of 0, which is 0, right? And the bottom goes to 0, right? So this is of the form 0 over 0, and we can use L'Hopital's rule to calculate this limit, right? That is, we calculate the derivative of the numerator and the derivative of the denominator, right? And then that the limit stays the same, right? So what is the derivative of sine? The derivative of sine is cosine, right? Pi over n. But then we're using the chain rule, right? What is the derivative of the inside input to the cosine function? Is going to be pi times 1 over n squared negative of that, right? And what is the derivative of the denominator, right? It's going to be minus 1 over n squared, right? Now, if you notice, the 1 over n squared cancels on both sides, and the minus sign cancels on both top and bottom, right? So this is equal to the limit as capital N goes to infinity of pi cosine of pi over n, right? Now, this limit we can take, right? And it turns out to be pi times cosine of 0, which is equal to 1, basically, right? So which is equal to pi times 1. So indeed, this limit, right? So the limit as capital N goes to infinity of pi sub n is indeed equal to pi, which is something that we expected. And then we have a formula that approximates pi in terms of the sine function, right? Now, sine is a transcendental function, which is another function that's difficult to calculate, right? So, but with modern computers, it's not so bad, but it's not a practical way of calculating pi. However, it's a way to illustrate calculus and geometry on how to approximate pi. Now, the next method is using the same idea, but instead of looking at the perimeter, we look at the area, right? So let's go into method number 2. Yeah, so approximating areas of circumscribed. I'm going to learn to spell again, but regular capital n-gons, right? So once again, we're going to look at the slice of the n-gon, right? it goes like that. It's got an angle theta, which is equal to 2 pi over capital N. And we want to do this area, right? So now remember, this is theta over 2, which is pi over N, right? And this is the radius r. Well, let's make that black because it's a known quantity, right? Now we have the base, no, the height actually, and the base, right? Base over 2, base over 2, right? So we already know what base over 2 is, right? It's 2r, well, it's r times sine of theta over 2, right? Which is equal to r times sine of pi over capital N. So that means that the base itself is going to be equal to 2r sine of pi over N, right? And what is the height, right? The height of this isosceles triangle is going to be r times cosine of theta over 2, which is equal to r times cosine of pi over N, right? So the area of this isosceles triangle, right? So the area AN, right? It's going to be equal to base times height divided by 2, which is 2r squared cosine of pi over N times sine of pi over N, right? Now, if you remember the double angle formula for the sine function, right? As an aside, right? The sine of 2 theta equals to twice cosine of theta times sine of theta, right? So this is equal indeed to r squared times the sine of 2 pi over capital N, right? And here we go. We might have made a mistake, but bear with me. Yes, so I think we're on track. Now, yes. 2 pi over N is pi over N, right? So yes, that seems to be okay, actually. Am I on track? Yeah, so it's twice r sine of theta, okay? Okay, so now the area of the nth circumscribed regular n-gon, right, is going to be capital N times AN, right? Which is equal to N r squared sine of 2 pi over capital N. And I think I have made a mistake somewhere. Maybe I haven't. Yes, oh, divided by 2. That's what I did. I forgot to do the divided by 2 part. So the 2's cancel, right? And then, well, forget it. So then that would mean that this is equal to divided by 2 as well. So, and this is divided by 2. Okay, there we go. So that is the area of the nth circumscribed regular n-gon. So how do we define pi, right? Pi is going to be equal to the area of the circle divided by r squared, right? Which is equal to pi r squared divided by r squared. So it does indeed check, right? So, but in this case, we're going to approximate it as the area of the nth circumscribed regular n-gon divided by r squared. So, which is equal to, well, I should probably not call that pi n. So let's call that something else. So let's call that bn, right? And then this would be bn, right? So, which is equal to n over 2 r squared sine of 2 pi over capital N. divided by r squared, right? So the r squares cancel. So we're going to look at the approximating area, right? So pi is going to be the limit as capital N goes to infinity of bn over r squared, which is equal to the limit as capital N goes to infinity of n over 2 times sine of 2 pi over n, right? Which in this case, this is equal to the limit as n goes to infinity of sine of 2 pi over n divided by 2 over n, I guess, right? So once again, this limit is of the form 0 over 0, right? Because as n goes to infinity, the numerator goes to sine of 0, and the denominator goes to 0. So we can use L'Hopital's rule to calculate the limit, right? So we calculate the derivative of the numerator. This is by L'Hopital's rule. It's going to be cosine of 2 pi over capital N times minus 2 pi over n squared, right? Divided by minus 2 over n squared, right? So the n squares cancel, the 2's cancel, the minus cancels, right? So I end up getting the limit as capital N goes to infinity of cosine of 2 pi over n times pi, basically, right? And that can be calculated easily, so it's going to be pi times cosine of 0, which is equal to pi. So indeed, what we've shown is that the ratio of the areas, right? So, I mean, the areas of the circumscribes regular n-gons do indeed approach the area of the circle, and not only that, they can be used to calculate a function whose limit is pi. And that function is given by this limit right here. So it's another way to calculate pi. Yeah, so it's not that much different than the perimeter method, but it's instructive. So now the next method is a probabilistic method. It uses well, it's known as well, it's a Monte Carlo method in the sense that you're using a probabilistic experiment to calculate a probability, which at the end of the day gives you the value of pi in one way or another, or using the formula, right? So, but this was known in the 1700s by a Count of Buffon in France. I'm going to show you a Wikipedia page eventually, so that you get acquainted with this picture. But the name of this method is called Buffon's experiment. And let me explain how I need to spell again. Sorry about that. Experiment. So let's do this again, right? So yeah, we did it again. We did it again. So, but let me explain how the method works. So we're going to have a piece of paper on the floor, right? And here's my piece of paper. And I'm going to draw vertical lines on it, right? So the vertical lines are going to be on it, and they're going to be equally spaced, right? The distance between vertical lines, we're going to call it t. So they're all equally spaced by a distance t, right? And separately, right, on the side, we're going to have a cup full of needles. The needles are going to be there, right? So needle 1, needle 2, needle 3, right? We're going to have their capital N needles, right? Needles. If I can spell it too, that would be nice, but I think I can do it. Um, A needle is going to have a length L, right? And we're going to assume that L is less than T. That is, the needle is less than the length of the needle is less than the spacing between the vertical lines on this piece of paper, right? And this is how we do the experiment. We're going to throw the paper on the floor, right? We're going to assume the paper is big enough, right? It's huge, but and these are the vertical lines. And then we're going to dump the needles onto the paper. Here's one needle. Here's another needle, right? Here's another needle. And it's going to be a random drop, right? So it's important that it's a random drop. At the end of the day, right? Well, after you've dropped the needles, not at the end of the day, but the needles are going to land on the paper. And we're going to assume that the paper is big enough so that then all the needles land on the paper. So that's important, right? So no needle lands outside the paper. And here we go. So here's a picture of what it looks like, right? Here's one needle. Here's another needle. Here's another needle, right? Here's another needle. And here's another needle, right? Some needles are not going to touch a vertical line, but some will, other needles will, right? So here's a needle that didn't touch a vertical line. Here's another needle that did not touch a vertical line, right? And what we're going to do is count those needles that do touch a vertical line. So here's one needle that touched a vertical line. Here's another needle. And here's another needle as well, and another needle, right? So, and then we're going to do this ratio. We're going to calculate the probability of a needle hitting a vertical line. So, hitting a vertical line, right? So in our example, there is 4 needles, right? So P, right, is going to be equal to number of needles that hit a vertical line divided by the total number of needles, right? And I need to do this again so that it works better. Great. So in this example that we just did, it's a random thought experiment. I mean, that ratio is going to be equal to 4 because there's 4 needles that hit the vertical lines. And the total number of needles is 4 plus 3, right? So it's 7, right? So this probability is 4/7, right? 4/7. Now the idea is that you increase the number of needles and you repeat the experiment several times, maybe 100 times, I don't know. And you keep calculating this probability, right? And the idea is that this probability is going to approach a certain number. Every time you repeat the experiment with the same capital N, the probability will start approaching a certain number, right? If you increase the capital N, the probability will change, but it will get closer to a certain number. So the bigger the N, the better it is. The number of times you repeat the experiment, the better it is, right? No matter what, as you increase, let's say, N, right? A number of trials, this probability will start approaching a certain value. basically. And that value will have us a relationship to pi. So we're going to calculate what that relationship is, right? So, right. So before we start that calculation of that probability, right, let us parameterize a needle, right, relative to a vertical line. So we're going to parameterize needles, the needles on the piece of paper, right? Piece of paper. We're going to parameterize them. And and then what we're going to do is calculate so this parameterization is going to depend on two variables. And then we're going to call those two variables random variables, right? Now, because those random variables don't have a preference on their values, because the needles are dumped onto the paper randomly, that will make them uniformly distributed. So those random variables are going to have a probability density function that's easy to calculate, right? So we're going to calculate that probability density function, and then using that probability density function, we're going to calculate the probability of a needle hitting a vertical line on the piece of paper. So that's the idea, right? So let's do the parameterization first, and yeah, so the parameterization, right? So let's do a random genetic needle, right? So here's the needle. So it just fell there, right? That needle is going to have a center of mass. So the center of mass is going to be at in the middle of the needle, right? So remember, the needle has length L, right? So this will be L over 2. This will be L over 2. The distance between vertical lines is little t, right? Now, we're going to calculate the distance of the center of mass to the nearest vertical line, right? So that will be x. And the angle that the needle makes with that distance, right? With the line that separates the center of mass to the nearest vertical line, we're going to call that theta, right? And these are going to be our two random variables. So x is going to be distance of the center of mass of needle, right? Of the needle, I get the needle, actually, if I can say that correctly, to the nearest vertical line. Right? So now theta is going to be the angle between the line that defines x and the needle itself. And the needle, right? Now let's talk about ranges of these variables, right? So x, right? It's easy to know, right? X is going to be either at least 0 and at most t over 2, right? Right. Well, not quite, actually. Let's see. Yes, it's at least 0 or at most t over 2, right? Because if the center of mass is right in between the two vertical lines, right, and the needle falls flat or rotated, right, then x is going to be t over 2, right? But if it's a little bit to the left, then the line goes, you don't draw the line from to the right, you draw the line to the left, and now that x is less than t over 2. So yes, so yes. But anyways, what I'm trying to say is the following, right? So here's an example of a needle that fell on the right side, on the rightmost side, right? So not that actually. One second. Here's the half side, right? So this needle fell on the right side of the spacing in between two vertical lines, right? So x in this case is less than t over 2, right? But if it fell on the rightmost side, right? Then this is x, right? This is the center of mass. And this will be the distance right here, right? So you will draw the line to the left instead of to the right because it fell on the leftmost side. The center of mass is on the leftmost side of the spacing. So x in this case will still be t over 2, right? So it makes sense that the range of x is between 0 and t over 2, right? But this now a similar argument, or if we think about it, right, the value of theta is going to be between 0 and pi over 2, right? So these are the ranges of the random variables. But let's see why theta is between 0 and pi over 2, right? It obviously makes sense that theta is between 0 and pi over 2, but could theta be greater than pi over 2? Just remember how we define the random variables, right? So let's draw a scenario, right? Remember how we define x and the line that defines x, right? So if the needle, right, falls, let's say, like this, right? And the center of mass, let's say, is to the right of here's x, right? So it's on the rightmost, right? Well, let's do this more obvious, actually. Here's my needle. Actually, here's my needle. And here is x, right? Now, here's the line. So since this needle fell on the rightmost side, right? What should pi be? I mean, what should the angle be, right? It would make sense that the angle is this angle right here, right? It could be this angle, right? Which is greater than pi over 2. But in this case, we're going to choose the angle to be this. So it could also be theta prime, which is less than pi over 2, right? So we choose the smaller angle, right? So if theta happens to be greater than pi over 2, right? Then the other angle along the needle, right, will be less than pi over 2. So the angle that we choose is the smaller of the two, basically. So it comes down to the following, right? The way we've defined theta, it's a little bit ambiguous, right? Ambiguous. It's the angle between the line that defines x and the needle, right? There are two angles that define there are two angles between the line that defines x, theta and theta prime and the needle, right? So what we should really be saying is since there are two possible angles, theta is always the smallest, is always the smaller of the two, right? Now, because we've chosen theta to be the smaller of the two, right? Then we know that theta will always be less than or equal to pi over 2. Okay, so now that we fixed the definition and we know the ranges of these random variables, now comes the next step, right? these random variables are uniformly distributed because there's no preferred angle for theta, and there's no preferred value for x, right? Where we are dumping the needles randomly onto the piece of paper, and because of it, we have there's no preferred value for x, and there's no preferred value for theta. So once we make that argument, right, we can calculate the probability density function of x and theta, right? So f of x of little x, right, is going to be equal to, since it's uniformly distributed, right, it's going to be equal to 2 over t, right? Why is that? Because the integral between 0 and t over 2, right, of f of x dx must be equal to 1. And this particular value will force that integral to be 1. So, right, so same thing for theta, right? It's going to be 2 over pi. As the integral from 0 to pi over 2, in this case of f of theta, the theta must equal 1, right? Now, if you choose this constant, this integral will indeed be 1, basically. So now that we have the probability density function for x and theta, let's ask the question, when does a needle hit a line? So and the answer will come from a geometric inequality, right? So let's draw a needle hitting a line, basically, right? So here we go. So here's two vertical lines, and let's draw a needle hitting a line, right? So here's one needle hitting a line. So here will be x, right? And this is the line, right? Now, well, maybe this is not a good example because it's too small. So here's the needle hitting a line. And let's erase these two things. Here's the center of mass. Actually, let's draw the orientation differently so that it's not that confusing. So here's one, here's x, and here's, so this would be x, right? And this would be theta, right? And you see what's going to happen is that this x, right, since the needle hit this vertical line on the right side, right, the needle will go over the vertical line, and this triangle, right, which is a right triangle, right, will have some part of it missing, uh, because x won't be able to complete it, basically. The line that defines x won't be able to complete this right triangle, right? So let's calculate the base of this right triangle, right? The base of that right triangle is going to be, now this hypotenuse is L over 2, right? So it's L over 2 times the cosine of theta, right? Yes, right? Now, well, how do I put this? Now, as long as that base is greater than or equal to x, right? Then we know for sure the needle has crossed that vertical line. So now, did I do this correctly? Yes. Yeah, it's the smallest of the two angles. So yes, so right. So this is the condition, right? L over 2 times cosine of theta has to be greater than or equal to x. Right, so when this condition is met, then we know for sure that a needle has crossed a line. Needle has cross the vertical line. Okay, so now that we know that, let's calculate the probability, right? So the probability. Oh wait, before we do the probability, right? Let's do the the density function, right? Now, one thing I forgot to mention is that as random variables, theta and x are independent, right? Because number 1 and 2, right? They parameterize a needle that falls on the paper, right? And they're independent because x cannot depend on theta. If it did, right, then somehow, then this will be a one-dimensional problem, right? But since the needles are landing on a two-dimensional piece of paper, you must need at least two variables that must be independent. So I mean, that's kind of my waving hand argument that they are independent, but it follows the reasoning follows those lines basically. So now since they're independent variables, right? That would mean that the density function of f(x) of x and theta, right, is going to be the multiplication of the density function of x times the multiplication of the density function of theta, right? Which is going to be equal to pi over 2 pi and then 2 over t, right? Which is 4 over pi t basically. Now, the probability of hitting a vertical line. So let's call that little p, right? Now we're going to do, it's going to be a double integral, right, of the density function of x and theta, right? X comma theta. Let's call this dx d theta, right? Now x is going to go from 0 to L over 2 times cosine of theta, right? And theta is going to go from 0 to pi over 2, basically, right? That is, we're not calculating the full probability over the state space, right? We're only calculating the probability or the density function. We're integrating the density function for a section of the phase space that corresponds to the instances when the needle crosses a vertical line. So yeah, so x has to go from 0 to L over 2 times cosine of theta, and theta has to go from 0 to pi over 2. So we get that double integral for that probability. And so this is equal to 4 over pi over t, right, times the integral from 0 to pi over 2, integral from 0 to L over 2 cosine of theta, 1 in this case dx d theta, because that probability density function of random variables is a constant, right? So this is going to be equal to 4 over pi over t, integral from 0 to pi over 2 of L over 2 cosine of theta d theta. So this is going to be equal to 4 over pi t L over 2 times the integral from 0 to pi over 2 of cosine of theta d theta. The 4 cancels with the 2, right? So you get a 2 over here. The integral of cosine is minus sine, right? So yeah, so is that really true? Yeah, well, let's see. Integral of pi over 2, right? So is cosine goes to 0, right? So that's a positive area. So no, the integral of cosine is sine, right? Because the derivative of sine is cosine, right? That much is true, right? So L over 2 over pi t, and it's going to be sine of theta from 0 to pi over 2, right? Well, sine of 0 is 0, sine of pi over 2 is 1, so this is equal to 2L over pi t times 1. So little p is going to be equal to 2L, 2 over pi, right? 2L over pi t, basically. So, right. So if we were to do the Buffon experiment, right? Then the probability that we will calculate from the Buffon experiment will be little p, right? Which will be number of needles that hit a vertical line divided by capital N, which is the number of needles, right? So how do we calculate pi out of this probability? We use this formula, right? So this formula will be used, right? So the way it's written is that 1 over pi is approximately equal to, right? L, well, it's actually T over L, so never mind. Over 2L, basically, times number of needles that hit the vertical line. I don't know. Divided by capital N. So this is how we calculate pi using this experiment, which is a probabilistic method, or also known as a Monte Carlo method. Right, so now it's interesting to see how a probabilistic experiment can calculate pi, right? Another interesting part is that you can actually write a computer program to simulate this experiment and then calculate this limiting behavior of 1 over pi. And that's something that will be an interesting project to pursue if you're interested in learning more about programming and the calculation of pi. Anyways, I hope you enjoyed this introduction or calculations, and please leave me any constructive criticism or destructive, anything that will help to improve the presentation. That will be great, actually. Thank you for watching. Have a good day.